All right, so the last thing that we have to talk about is called Hess's Law. And this is going to combine kind of what we learned in kinetics, Unit 5, with all of our reaction mechanisms, all of the steps that add up to the overall reaction. We're going to do that, but now we're going to manipulate the steps in order to solve for the total change in enthalpy for an entire reaction. Okay, so it all relates back to the fact that enthalpy is a state function. So that means that when you're trying to go from a particular set of reactants to a particular set of products, the change in enthalpy is the same, whether the reaction takes place in one step or a series of steps. So Hess's law helps us when we have that series of steps, where what we do is we add up all of the change in enthalpies for each reaction step to create an overall change in enthalpy. So there's a little bit more information listed in our textbooks on those pages if you want to check it out. I will also be posting on It's Learning an additional video in case you, from somebody else, in case you need some more help with this, because you just kind of have to jump in to try and solve. Okay, so what we're going to do, right, we're going to have all of our reaction mechanism, all of our steps listed, and every step will have its own change in enthalpy. Sometimes, though, we will have to manipulate the equation steps in order to get the overall reaction that we need. So sometimes, like if something that's important is on the incorrect side of the arrow, like maybe it should be a product, but it's currently a reactant, and the reason why it might be a reactant is because the way that our enthalpy is listed for endothermic versus exothermic, right? So we might have to reverse the reaction to get it on the right side, on the correct side. So when I say reversed, I'm really talking about that we're going to flip the reaction around, okay? And so when you flip it around, literally going reactants turn into products, products turn into reactants, then we also change the sign on the change in enthalpy of that reaction. Then also, sometimes the coefficients are not correct. So the number value, the magnitude of the change in enthalpy is directly proportional to the quantities of our reactants and products. So if we need a coefficient of 2, but it only has a coefficient of 1 to start, then when we multiply by 2 to get the correct coefficient, we also would multiply the change in enthalpy by that same amount. Okay, so those are some things. Now, it can be overwhelming. This first one we're going to start with, for example 11, is not so bad, but we are going to start, and then example 12 is going to be a big one. So when you're doing this, the best strategy is just to work backwards, right? So you're going to be given the overall reaction that you're supposed to be getting, and so I would just start with the reactants and just make sure this reactant is in the correct spot. If it's not, maybe reverse it if it needs it, or if it needs to be multiplied to get the correct coefficient, do that, and just work one by one through all the way, okay? And then it's important to note, just like it was in in Unit 5, if they're on opposite sides, they can cancel out or subtract from each other if they don't have the same coefficient. And if they're on the same side, they multiply, or they add together. So they would increase the number. So there's all different kinds of these problems that you could do, numerous numbers of steps for that. But let's just get started. We'll get started with an easy one. So we have 2 forms of carbon, graphite and diamond. So the reaction is given to show that the graphite turns into carbon. And we want to know the change in enthalpy for that conversion. So we're going to find what is the change in enthalpy for this overall reaction, okay? This right here. So looking at our 2 steps that we have, one of them involves graphite, one of them involves diamond for their combustion. This is how we found some changes in enthalpies for them. So what I do first is I just look at the top reaction and say, okay, my graphite needs to be a reactant and it needs to have a coefficient of 1. Okay, so in our 2 steps, I've got graphite that is a reactant and it has a coefficient of 1. So that means that we are not going to do anything to this reaction it's already good enough. Now, like the O2 and the CO2, those are eventually going to cross out, right? Because they're not in the overall reaction that we're trying to achieve. So don't worry about those for right now. Just look back at the overall reaction. So then next, we need diamond on the product side with a coefficient of 1. Well, currently diamond is on the reactant side. It does only have a coefficient of 1, but it needs to be on the other side. So I usually write down little notes myself about what I did. So we need to flip the diamond reaction so that the diamond can go to the product side. Okay? So I like to cross it out so I don't look at it anymore because I can get confused. So the CO2 will become the reactant. And the diamond, I'm just going to put DIA for diamond, plus O2 will become product. And so since we flipped the reaction, then that means that we changed the sign for the delta H. It was negative 396, so now it's a positive 396 kilojoules. Okay. So at that point now, diamond is in the correct side, it's on the correct side, and has the correct coefficient to get where we need to go. Okay. So then we're now finished with this second reaction. Okay, since we've manipulated all the reactions possible, then, and we've looked at all of them, then right now, as it stands, we should be able to add together and get the overall reaction. So if I add this together, I've got my graphite. Okay, now let's talk about this O2 and the CO2. Okay, so I've got the O2 in the first reaction on the reactant side, and I've got the O2 on the product side. They both have a coefficient of 1, so both of those can cancel out. Okay, then the CO2 and the CO2, both coefficients of 1, those two can cancel out. We can get rid of all those. So then the only thing that's left now is our diamond, which is what needed to happen. So now we've got our overall reaction, what we needed. So then to find the change in enthalpy for the reaction, we just add up the numbers as they have been written, as we've manipulated them. So negative 394 plus 396, that equals 2. Now, for significant figure rounding here, usually at the end, you are just going to add them together or subtract. So when we round these, you just round to the lowest number of decimals. That's the rule for adding and subtracting. So usually it'll just be a whole number, and that's why 2 significant figures is the correct answer. Okay, now this 2, this is the whole thing. This is the whole point of the problem. We wanted to calculate the delta H. Okay, but in order to do it properly, you have to manipulate all of the steps. And if you don't manipulate the steps correctly, you might not get that right answer. Okay, so this one was simple. Now let's do a difficult one. So diborane, which is the B2H6, is a highly reactive boron hydride that was once considered as a possible rocket fuel for the U.S. space program. We want to calculate the delta H, so we're going to overall reaction, find it for this reaction right here, for the synthesis of diborane from its elements, according to that equation. Okay, so we've got 4 steps here, all right? Don't get overwhelmed. We always just start with the overall reaction, because that's what we're trying to achieve. And all of the extra steps, like if you notice, we've got some things that need to cancel out in this reaction. That's okay. They will eventually pass out. We just have to work with that overall reaction first, okay? So the first reactant, I see a 2B. It needs to be on the reactant side, the boron solid, and it needs to have a coefficient of 2, just boron by itself. Well, in the first reaction, we've got boron by itself, and it's on the reactant side. So that means that this is good to go. Sometimes I did it in the last reaction without telling you. If it's something that's like where it needs to be, I will box it so that I remember if that's where it needs to be. I can't do that. And then I also usually like to write down like no changes. so that I don't go back and try to change it, because I know that's where it needs to be, and I shouldn't change anything because of that. Okay, so now if you want to just leave that, you can, but for myself, I don't have any more space to write anything on this slide, so I'm going to write it real quick on this slide, and I'm going to go ahead and just do like 1, 2, 3, 4, so that if I need to change anything else for any of the other reactions, I'll put them in that same order. This isn't necessary, but just trying to help you out, okay? So that first reaction, we're feeding it 2B plus 3 halves O2. Don't get freaked out about the 3 halves. It'll be okay. B2O3, and we're going to keep the delta H to be negative 1273. Okay. So that one is done. Okay, the next reactant that we need is 3H2. So we need H2 on the reaction side, and it needs a coefficient of 3. Well, looking at the reactions, H2 is in reaction number 3. It is on the correct side of the equation. It is a reactant, but it does not have a coefficient. It only has a coefficient of 1, and we need 3. So not only are we going to multiply the H2 by 3, we're actually going to multiply everything in the equation and the number all times 3. Okay, so I'm going to rewrite this on my next slide, putting coefficients times 3. Okay, so that means that we've got 3H2 plus, and it was 1/2 O2, so that turns into 3/2 O2 to make 3 waters. Now, if you haven't noticed yet, the fourth equation has 2 different types of water, water liquid and water gas. So I'm going to be careful to label this water liquid, because that's going to be important at the end, because we want no waters when we're done, so we just want to make sure everything cancels out. Okay, then the new delta H, it's negative 286, times 3 is negative 858. So that is reaction number 3, done. We've got this where it needs to be, and we got the correct coefficient in front of it. All right, we're going to box that one. Okay, so looking at our overall reaction, that's all the reactants we need. So now we just need one product, the B2H6, the diborane. So it needs to get the product side, it needs to have a coefficient of 1. Well, looking at our reactions, reaction 2 has it. It has the correct coefficient, but it does not, it's not on the right side. It's not on the product side. So that means that we're going to flip this whole reaction. And when we flip the reaction, that means we change the sign on the number, okay? So here we go, flipping it around. I'm going to just write it, products first, reactant second. So B2O3 plus 3H2O gas, and I keep that in there. Now arrow goes to B2H6 plus 3O2. And the change in enthalpy was negative 2035. So now it's going to be a positive 2035. Okay, so that B2H6 is now in the correct spot, and it has the correct coefficient by flipping things around. Done right there. Okay, now that's all we have in our overall reaction, but we haven't even touched this fourth equation yet. And the reason why the fourth equation is there is just so that we can cancel out our liquid and gaseous water. Okay, now currently we got liquid on the left, gas on the right. Will that cancel everything out as needed? So they have to be opposite sides, right? So looking at my newly changed reaction, I got the gas on the left and the liquid on the right. So in my fourth equation, liquid has to be on the left, gas has to be on the right. And it is such as that. So this one will have no changes. And it's simply here so that we can cancel out all of the waters. Okay? But, oh wait, time out. There are no changes. That's wrong. Those have coefficient of 3. Goodness, I forgot to see that. So they both have coefficient of 3. So that means we will have a change. We're going to multiply by 3 for this whole reaction. Not flipping, but just multiply by 3 so that we can get what we need. So we'll have 3 H2O liquid turn into 3 H2O gas. And then the delta H, it was 44 times 3, 132 kilojoules. All right. So now we've touched all 4 reactions, so theoretically things will work out when we add things together. Okay. I will change my color of my pen so that we can see things in a different light. Okay. Let's try to cancel some stuff out. So the B2O3 right here will cancel with this B2O3. That's good. And then we talked about like the 3 H2O gas will cancel out and the 3 H2O liquids will cancel out. Let's talk about these O2s. We've got 3 halves O2 and 3 halves O2 both on the reactant side. So 1.5 plus 1.5 would equal a total of 3 oxygen gases overall, right? Because they're on the same side as the F. Well, that 3 overall will balance with those 3 overall so that everything will cancel out. That one's the tricky one when you have to like add them together in order to cancel out the other side. That gets tricky. I understand that. But that's all that we have to cross out. So we have got 2B plus 3H2 to make B2H6, which is our overall reaction we wanted. So to find the change in enthalpy for the reaction, we just add up these numbers, or subtract, as is, rounding to a whole number, we'll get a positive 36 kilojoules for the answer. For the label, or for the unit, I would just label it whatever the delta H's are originally recorded in. Totally fine. Unless it tells you something specifically different, that'll be okay. So that is a more difficult example of Hess's Law. We had some textbook problems, but I will be posting another video on its learning for some help if you need to see some more practice.